The realm of artificial intelligence is expanding at an astonishing rate. Large language models are becoming increasingly sophisticated. They can generate human-quality text, translate languages, and answer complex questions. However, their true potential lies in their ability to interact with the world beyond text. This is where tools come in, offering LLMs access to vast repositories of data and powerful functionalities. But there's a catch. Each tool often speaks a different language, requiring a unique integration effort for every LLM. Imagine the complexity of connecting hundreds of LLMs with thousands of tools. This is the NXM problem, a scaling nightmare that threatens to stifle AI's progress. It's like trying to build a tower to the stars using a different type of brick for every inch. We need a universal connector, a common language that allows AI and tools to communicate seamlessly. This is where the model Contextual Protocol steps in, offering a beacon of hope in this complex landscape. MCP provides a standardized way for LLMs to connect and interact with external tools, regardless of their underlying implementation. It's like giving every builder the same blueprint, allowing them to work together towards a common goal. MCP's impact on the AI industry is profound. By eliminating the need for custom integrations, MCP drastically reduces redundant development efforts. Developers can focus on building innovative tools and applications rather than reinventing the wheel for every LLM connection. This standardization also simplifies maintenance and ensures more consistent implementations. Imagine a world where every AI-powered application can seamlessly access and utilize any tool it needs. This vision is becoming a reality thanks to MCP's elegant client-server architecture. On one side, we have the MCP client, often embedded within a host application like an AI assistant or a code editor. The client acts as an intermediary, translating requests from the LLM into the standardized MCP language. On the other side, we have MCP servers, each dedicated to a specific tool or data source. These servers expose their functionalities as a set of capabilities, allowing LLMs to discover and utilize them through the client. Connecting the two is the transport layer, which can be as simple as standard input/output for local interactions or leverage HTTP and server-sent events for remote communication. All communication adheres to the JSON RPC 2.0 specification, ensuring interoperability across different platforms and programming languages. The beauty of MCP lies in its simplicity and clarity. Let's break down the interaction flow into smaller, more digestible steps. When an MCP client connects to a server, they engage in a handshake process. The client communicates its capabilities and requirements, while the server responds with its own set of functionalities. This ensures that both parties are on the same page and can understand each other. A user interacts with an AI application, prompting the LLM to generate a response. During its processing, the LLM identifies the need for external data or functionalities to fulfill the request. Based on the user's request and its own internal logic, the LLM selects the most appropriate MCP capability from the available options. This could involve accessing a database, calling an external API, or retrieving information from a knowledge base. Before executing the chosen capability, the MCP client prompts the user for permission. This ensures transparency and gives users control over how their data is accessed and used. Upon receiving user authorization, the client and server communicate through a series of JSON RPC messages. The client sends requests, receives responses, and may even engage in real-time data streaming, depending on the specific capability being utilized. The LLM receives the requested information or the result of the executed function from the server. It then incorporates this external data into its response generation process, ultimately providing the user with a richer, more informed answer. The adoption of MCP is rapidly gaining momentum, leading to a thriving ecosystem of clients, servers, and integrations. Popular AI applications like Claude Desktop, Zed, and Cursor are integrating MCP clients, allowing their users to seamlessly leverage the power of external tools. On the server side, we see a diverse range of offerings, from reference servers for databases like PostgreSQL and communication platforms like Slack, to official integrations for services like Stripe and JetBrains. Of course, security is paramount when it comes to AI and data access. MCP addresses this concern by employing industry standard OAuth 2.1 for authentication and authorization. This ensures that only authorized users and applications can access sensitive information. Furthermore, MCP encourages a human-in-the-loop design requiring user consent for potentially sensitive operations. This approach, coupled with the principle of least privilege, minimizes the risk of unauthorized data access. Looking towards the future, MCP has a bright and promising roadmap. Efforts are underway to establish an official MCP server registry, providing a centralized repository for discovering and connecting to various tools and services. Additionally, there's ongoing research and development into sampling capabilities, allowing servers to request LLM completions, further blurring the lines between AI and traditional applications. As MCP continues to evolve, we can expect even more innovative features and a robust, secure ecosystem that empowers AI to reach its full potential.